So, this is Barrelfish, and we're talking about the multikernel, which is a new OS architecture for scalable multi-core systems. And in particular, what we're trying to address in this work is we're trying to answer the question of how to structure an operating system for future multi-core systems. We see two key challenges here. The first is basic scalability to large numbers of cores that may increase at rates approaching Moore's law. But secondly, there's a challenge with heterogeneity and hardware diversity. So what do I mean by that? Here's three examples of multi-core processors on the market today, or soon to be on the market. On the left here you have the Niagara, and that has a banked level 2 cache that is equidistant from all the cores on the chip, which means that shared memory algorithms that access the same regions of the cache will perform well, will scale well across all those cores. On the other side, you have the Opteron, which has a large, slow shared L3 and private L2s, and the access latency to the shared L3 is almost double the access latency of the L2. And the upcoming Becton, which will have a banked cache and a ring network inside the chip to access different cache lines inside the chip. And so the important point here is that the way that you optimize shared data structures for these three processes is completely different. And things that scale well on the Niagara won't scale well on the other two. Another instance of hardware diversity is the interconnects that you see between the chips in a box. This is an example of a 32-core AMD system we have in our lab. You can see that those blue hypertransport links between the different sockets make for a pretty interesting network topology, and they also play into the performance and the scalability of the system. But that's just that system. There are many other topologies that you can have. This is again, the forthcoming 8-socket Nehalem machine, has a completely different interconnect. And as these things move onto chip, you'll start to see more of these kinds of networking effects inside the chip. So on the top here is the ring network on the Larrabee, and on the bottom you can see the mesh network on the Tylera processors. And there's lots of different models for how these things will be interconnected. And they play into the access latencies and the performance behavior of these systems. Finally, there's core diversity, either because you have different kinds of cores in one system. So in machines today, it's quite likely that you will have programmable network interfaces, for example, with ARM cores on them, GPUs, FPGAs. You can put FPGAs in the hypertransport sockets in that system that I showed you before. And it seems likely that in the near future, there will be systems with asymmetric cores on a single die, either because those cores will have different performance characteristics. For example, it's likely that you will have a small number of large, fast, power-hungry cores and a much larger number of smaller, simpler, slower cores. Or because some cores might not support the full instruction set. For example, they might leave out streaming instructions or virtualization support. And in all of these cases, we see that not only are there increasing core counts, but there's also increasing diversity within the system and between different systems on which the operating system has to run. And this diversity is a real challenge because unlike many past cases of scalable systems, where, for example, in the HPC space, you've designed an algorithm or an application for a particular machine, it's going to be much harder to optimize these things at design time as these systems move into the general purpose computing space. So we think that there's going to be a need for system software to adapt to the hardware on which it finds itself running. And so we think that because of all these trends, now is a good time to rethink the default structure of an operating system. Today's operating systems are more or less by default a shared memory kernel that executes on every core in the machine, exchanges data through shared data structures that are protected by locks or other shared memory synchronization mechanisms. And anything that doesn't fit into this model, like offload processors, is abstracted away as a device behind some sort of primitive device API. And we think that a good way to address this, and it mirrors exactly something Barbara Liskov brought up at the end of her keynote this morning, is to see this heterogeneous network of different cores inside a system as a distributed system. And so we propose structuring the OS as a distributed system. And we call the model for an operating system structured in this way the multikernel. And so in this talk, I'm going to present three key design principles that we think make up the multikernel model: making intercore communication explicit, making the structure of the OS neutral to the underlying hardware, and viewing state as replicated inside the machine. And so then in the remainder of this talk, I'm going to introduce those principles before going on to Barrelfish, which is our implementation of the multikernel, and presenting one part of the evaluation from our paper. So the first design principle is making intercore communication explicit. And by that we mean that all communication between cores in the system happens with explicit message passing operations. So there is no assumption of shared state in the model. That's quite an extreme statement. In particular, it's a big divergence from the way people build OS code today. But if we can make that work, it has some big advantages. First, and most importantly, it allows us to decouple the structure of the system from the concrete details of the intercore communication mechanism between particular cores in the machine. And so communication patterns between cores in the system are expressed explicitly. That means that instead of optimizing shared memory algorithms, thinking about in which cache lines are likely to be local to my core, how do I optimize the locality of a particular data structure, you think about, to implement a particular operation, with which other cores in the system do I need to communicate explicitly? Message-based communication also naturally supports heterogeneous cores and non-coherent interconnects, such as PCI Express. Think about some part of an application running on an ARM offload processor on a network interface. It's a better match for future hardware, either because that hardware may support cheap explicit message passing, like the Tilera processors, where you can send a message across the mesh network in tens of cycles, or because that hardware may have limited or no support for cache coherence. An example of a system that fits in this category is Intel's 80-core Polaris prototype, where they didn't actually implement cache coherence in hardware because it was too expensive. Message-based communication allows an important optimization, which is that you can decouple the message, the operation that requests some remote service, from the handling of the response, which is the notification that some operation is completed or failed. And this split phase behavior is important for getting greater concurrency out of the system. Finally, we can reason about the performance, the scalability, and the correctness of systems based on explicit message passing. And so you're probably thinking, well, that's all very nice, but the machines that we have are fundamentally shared memory systems, and the performance of any message passing primitive is going to be horrendously slow, much slower than you can get with efficient shared memory structures. And what I'm going to show you now is a simple micro benchmark that we did just to try to evaluate this trade-off on current hardware. There are two cases. In the shared memory case, what we have is a set of cores that are all updating a shared array, read-write updates. And so what happens is when every core modifies the array, the cache coherence protocol of the processor has to migrate the modified cache lines around between all the cores that are performing the updates. And so while this migration happens, the processor is stalled, and the overall cost of the update is limited by the latency of these round trips across the interconnect to fetch or invalidate cache lines. And the overall performance of the update, in terms of the throughput of updates, will depend upon the data size in terms of the number of cache lines, and the contention in terms of the number of cores manipulating the state. And this is how it scales. This is what happens when every core modifies 1 cache line, 2, 4, and 8 cache lines. You can see that it's not scaling particularly well. What's interesting here is that as we're adding cores, every core is still executing the same number of instructions. They're directly manipulating shared state. There's no locking happening here. And so all of those extra cycles, the processor is stalled, blocked, waiting for the interconnect to migrate cache lines around. In the message passing case, we localize the state, localize the shared state on a single server core. And rather than the client cores directly manipulating the shared state, they express their update as a message, which they send through a shared memory ring buffer-based message channel that we've implemented on shared memory. And then the server core locally performs the updates and sends back a reply. In this benchmark, we're using synchronous RPC, so the clients all block while they're waiting for a reply from the server. Here's how it performs. You can see, and this is the case where the server updates a single cache line in response to every message. And this is the case where it updates 8 cache lines in response to every message. It makes very little difference because the amount of data we move across the interconnect is the same, and the data is all local to the server's cache. You can see that for this experiment, we're already better for 4 cores and 4 cache lines on this machine. But what's more interesting is that the reason that this is increasing here is due to queuing delay at the server. So the clients are blocked, waiting for the server to satisfy their request because the server is saturated. So if we measure the actual cost experienced at the server of performing the update, which is flat because the state is all local in its cache, we can infer that roughly the amount of cycles between those two lines are the amount of cycles that would be available to do other work if we had a split phase RPC primitive, if we could have the client send the request, and then do some other work and asynchronously handle the reply. And that's an important optimization, this split phase behavior in a message-based system, which is much harder to do in a shared memory system because you don't get to execute any instructions. You're waiting for the cache coherence protocol. Our second design principle is that we separate the structure of the operating system from the underlying hardware. So the only hardware-specific parts of the system are the message transports themselves, which are highly optimized and specialized to the details of the hardware interconnect that we have available. So in the example I just showed you, the message transport is micro-optimized to the details of AMD's hypertransport cache coherence implementation. And in the common case, it takes only 2 hypertransport requests to move a message. The other part of the system that's optimized to the hardware is, of course, device drivers and the stuff that interacts with the CPU. This separation allows us to adapt to the changing performance characteristics of the systems on which we run. And I'll give you an example of that later on. And it allows us in particular to late bind on the concrete message transport implementations and protocol implementations that are used on different systems. And we think that this separation of concerns is a good way to adapt to the hardware as it changes. Our final design principle is that all potentially shared state in the machine, and this includes anything that an operating system would typically be maintaining in shared memory, including scheduler run queues, process control blocks, file system metadata, so on, is accessed as if it were a local replica rather than a globally consistent copy. This is sort of naturally required by the message passing model. If you don't have shared state in your model, you need to send messages to maintain replicated state. The advantages of this are that it naturally supports domains that don't share memory. Again, think about the case where you have some application where part of the application is running on an x86 CPU and part of the application is running on an ARM processor on a NIC. And those 2 different parts of the application are both using OS services. It also naturally supports changes to the set of running cores because we're hot plugging devices that might have cores on them, or we're bringing up and down cores for power management reasons. We can use results from distributed systems to deal with the case where you have replicas on nodes that are coming and going. So, as I've presented the model so far, you can sort of see this progression of progressive approaches to scalability in operating systems where people have identified that sharing is a limitation on scalability, and they've progressively introduced replication as an optimization to help systems scale, to the multi-kernel being at the extreme endpoint on the far right of that, where we have no shared state at all and we execute replica maintenance protocols. In reality, there will be machines, there will be cases where it's much cheaper to share. An example of that is hyperthreads or cores that are tightly coupled sharing a cache between them. And so in reality, on a multi-kernel, we can use sharing as a local optimization of replication. And so you might just manipulate some shared state if the core that you're going to is very close. But the important point is that the model remains a split-phase replica maintenance model, rather than the model being sharing and the optimization being replication. And so when you put all that together, this is the model of a system constructed as a multi-kernel. Note that we can customize the operating system and the state that it maintains to the core on which it happens to run. And note too that we can support applications using shared memory. If the application wants to use shared memory and if the hardware supports it, that's perfectly fine. But we don't rely on it for the underlying function of the operating system. So, Barrelfish is our actual implementation of this. It's a from-scratch implementation of a multi-kernel. Currently runs on 64-bit Intel processors, but the beginnings of an ARM port are already booting, and it's open source. In Barrelfish, we factored the OS node into a privileged kernel mode portion called the CPU driver, and a privileged user domain called the monitor. And so the CPU driver serially handles traps and exceptions, while the monitor is responsible for mediating local operations on global state and actually executing the various replica maintenance protocols. Our message transport on current cache coherent x86 hardware is our implementation of URPC, and that's this ring buffer that I mentioned. But we fully expect that to change as hardware transports change. We expect to use different message transports between different cores. There's a whole set of other ideas in Barrelfish that are not directly related to the multi-kernel model, and I'm not going to talk through all of these now. Feel free to ask questions. But perhaps of particular note are that we decouple the message passing primitive from the synchronization mechanism. We use capabilities for resource management in the system using a model very similar to SEL4. And We're running many other OS services up in user level. Barrelfish has a whole set of applications running on it because we're trying as much as possible to build this as a real system. So you're looking at the slideshow viewer. It has a web server which survived a slash dotting a couple of weeks ago. We run virtual machines, shared memory microbenchmarks, database engine and constraint engine, a whole lot more on the way. So we're continuing to build Barrelfish and try to make it real. But enough of that. How do you evaluate a radically different operating system structure? Barrelfish, by mere fact that it's a prototype and it's from scratch, is necessarily less complete than an existing OS such as Linux or Windows. And so our goals when evaluating Barrelfish are really that it should have good baseline performance, which means that it's at least comparable to existing systems on current hardware. But what's much more important to us, at least, is that it be able to scale with core counts, be able to adapt to different hardware on which it finds itself running, and be able to exploit the message passing primitive for performance. So I'm going to show you one part of the evaluation from the paper, which is the case study of how we implement Unmap in Barrelfish. When you perform an Unmap operation, logically what needs to happen is you need to send a message to every other core holding some shared memory mapping. And you need to wait for them to acknowledge that they've locally performed the Unmap, they've invalidated the TLB or whatever else. On most operating systems, the way that this works is that the kernel sends interprocessor interrupts to all the other cores and then spins on some region of shared memory waiting for an acknowledgement that the Unmap has been performed. On Barrelfish, the way this works is that the user sends a local request to their local monitor, and then the monitors implement a single-phase commit across the system because that's essentially what an Unmap is. It's a single-phase commit on the TLB. And so the question is, how do we implement the single-phase commit? How do we implement this communication across the machine? We tried a number of different communication protocols for Unmap. In the Unicast case I'm about to show you, we have one URPC channel between the initiating core and all of the other cores in the system. And so we write the message once into every channel, they perform the Unmap, and then they acknowledge the response. In the broadcast case, we have a single channel that is read by all the cores. Neither of these actually perform particularly well. In particular, broadcast doesn't work well because cache coherence is not broadcast. When you write the message, it crosses the interconnect once to every receiver. There's no broadcast underneath. And so how can we make this go better? If you look at the topology of this machine, it kind of naturally suggests a multicast optimization. What you really want to do is send the message fewer times across the interconnect. And so what we do in this example is we send the message once to every socket rather than sending the message once to every core, which means that the same message crosses those hypertransport links many times. And so we send the message once to an aggregation core on each socket, who then locally sends it on to its neighbors, and that local send is much faster because all those cores share the same cache. There's an additional optimization, which is when we observe that some sockets will take longer to get to because there are more hypertransport hops involved. They're further away on the interconnect. And so you want to send to those sockets that are further away before you send to the local ones to get greater parallelism in the way the messages travel across the machine. And you can see that this scales much better. But it brings up an important point. In order to apply this optimization, we need to have a lot of knowledge about the underlying hardware. We at least need to know the mapping of cores to sockets, and we need to know the messaging latency so that we can send messages to the cores that are furthest away first. More generally, Barrelfish needs a way to reason about the diverse system resources and handle the diversity of the hardware on which it runs. And the way we currently tackle this is with constraint logic programming. So we have a user service called the system knowledge base that stores as rich and detailed a representation of the hardware information that we can gather or measure and allows us to perform online reasoning queries against it. And so we use a Prolog query on the system knowledge base to construct the appropriate multicast routing tree for the machine on which we're running. When we put all this together, this is how the Unmap primitive on Barrelfish performs. What's important here, I think, is not that Barrelfish is necessarily scaling better than Linux or Windows, because you could equally apply these kinds of optimizations to traditional systems. And you can also see here that Barrelfish is suffering from a fairly expensive message passing primitive to contact its local monitor. What's more important is thinking about this as a communication problem and thinking about how to implement a single phase commit on a particular system abstractly from how do I perform an unmap across the machine. That seems to give a better handle on being able to adapt the operating system to the hardware on which it runs and being able to scale the operating system with different hardware architectures. To very, very briefly summarize the other results in the paper, we can run shared memory workloads such as Splash and OpenMP with essentially no penalty, which is not very surprising because it's just exercising the hardware cache coherence mechanism. We have respectable network throughput and web server workload, web server performance. The main high-level bit from these results is not that Barrelfish is better than Linux or anything like that, because it's a very apples and oranges comparison. The high-level result for us is that Barrelfish performs reasonably on current hardware. And so we can conclude from this that there is no inherent performance penalty from building an operating system as a multi-kernel, and that there's the potential for being able to scale much better in the future. And so to wrap up, I've argued that modern computers are inherently distributed systems inside the box, and that it's therefore time to rethink the structure of an operating system to match this. I've presented the multi-kernel, which is our model for the operating system as a distributed system. It uses explicit communication and replicated state, and it tries to keep the structure of the operating system neutral to the underlying hardware topology. And I've also presented Barrelfish, which is our concrete implementation of the multi-kernel. It has reasonable performance on current hardware, but arguably more importantly, better scalability and adaptability for future hardware. And I think we can conclude that it shows that the approach is promising. Put in another plug for our website at this point. Please visit that. You can download the source code of the system. You can also find out a lot more information. And if you'd like to see Barrelfish doing anything other than splitting bitmaps to a frame buffer, please come along to our demo in the poster session tomorrow afternoon, where we'll have some visualizations going. With that, I'm happy to take questions. So there are two things I'll say to that. First of all, Barrelfish, we've been focusing on so far how to build the OS so that it scales. And so we don't want to make any particular demands on how you structure an application. We can support POSIX-style application programming models. But I think that clearly that's not the right way to build an application that will adapt to large numbers of different cores. And so the answer is going to have to be some higher level programming model, either languages, runtimes, things like MapReduce. There's a whole different set of ways to express this thing. And we think that a tight coupling between the runtimes for those kinds of programming environments and the underlying OS that can make use of hardware knowledge is the right level at which to do that.
Hi, Michael Johnson, PhD student at MSW. I have a question about your URPC performance. So in the setup of your web server and you look back benchmarks, you seem to distribute processes across the cores, and on one core you only seem to run that process and monitor and nothing else really. So it seems when you assign the URPC to that process, the process is mostly running and ready for that URPC message. So you're probably running into the case where you should take the performance hit and switch back to the correct process to actually receive the message. So the thing is, in a overall system, you will probably run into that case more often. So have you got any experience or comments on that?
That's true. So there are two things to say about that. We've made an explicit design decision to decouple the messaging primitive from a notification primitive, like an interprocessor interrupt or something like that. And that's because it's very expensive to perform notifications. So at least on our hardware, it costs something like 800 cycles on the sending side just to send an API, and more than 1,000 cycles to take the trap and handle an API. So you clearly don't want to do this for every message. And that's why we've made the decision to decouple those. And so then, given that you have that decoupling, you have a trade-off. You sometimes will need to send the notification because you have some operation that needs to be performed soon. For example, you may well make the decision for a given unmap that I need this unmap to happen now, and so I'm going to send the IPI and pay the extra cost of doing that. And our benchmarks don't show that. However, there will be many cases where you don't need to do that because you either don't need the result immediately, and the split phase API allows us to separate those things, or because you can wait for a time slice. And so there's a trade-off between time slicing latency and the message servicing delay for a particular domain. So our experience is that, yes, this happens, and if you run multiple things on a core, you have a trade-off between how much you time slice and how long it takes to service a message. And I can show you graphs that show essentially what you expect, right? As you adjust the time slicing duration or as you send an interprocessor interrupt, it affects the message latency. But I think it's important to decouple these things. I can hear you, so I could try to repeat it if you... I can't tell you for sure because we haven't run that benchmark, but I would expect that it's slower because as well as contending on the data, you first have to contend on the cache line with the lock. And there are various techniques to make the lock scale. The point of that benchmark is obviously having a whole lot of cores hammering on one region of shared memory is not a realistic way that people build shared memory structures. I grant you that happily. The point of that benchmark is just to make the case that you can actually implement messaging even over a shared memory transport, and it can have reasonable performance.
I was wondering about virtualization. If you don't mention it, let's say, for people are one year, so with regard to Barrelfish, with regard to virtualization, is no longer needed for something that is above more or less
I think we view virtualization as orthogonal to the problem of how you get system software to scale to a large set of cores. These kinds of challenges will either crop up in an operating system or they'll crop up in a virtual machine monitor that has to run VMs on a large number of cores. So you can see, in some sense, a virtual machine as a user process with a very particular programming interface to the OS. So I think it's a largely orthogonal problem.
One more question over there.
I think for the question, like the picture, as these systems get bigger and denser, do you expect messages to get lost or corrupted?
That's a really interesting question. So at least on current hardware, no, and in the foreseeable future, maybe. I think if messages do get lost inside the machine, this model of structuring the OS is a better way to handle that than a shared memory model. But I can't tell you whether we will have hardware that loses messages. Thank you.